The Northeast Atlantic is one of the most productive fisheries regions in the world, and the place where most modern industrial fishing originated. Statistics on catch in this region are available from the Food and Agriculture Organization of the United Nations, that is the FAO. The total catch reported to FAO is shown in this figure, and since 1970s has fluctuated between 9 and 13 million tons. But there's been a consistent decline since about 2000, so that the catch is now about 8 million tons. 174 stocks are assessed through the science process of ICES, and these assessments generally provide the history of catch, total abundance, spawning stock size, fishing mortality, and annual recruitment. The total catch represented in these assessments is shown in this figure. From 1950 to 1980, the ICES assessed stocks in that period covered roughly half of the total catch reported to FAO, since few ICES assessments began as early as 1950. However, since 1980, the assessments have covered 90% of the total catch reported to FAO from the Northeast Atlantic. Thus, through the science process of ICES, we have a good idea of the trends in the status of the fish stocks that make up most of the food production from the Northeast Atlantic, with almost total coverage of the abundance of stocks since 1980. A key feature of stocks and catch in the Northeast Atlantic is the great diversity in the size and potential catch of the fish stocks. Although there are landings data for 465 species or taxa of fish and invertebrates in the FAO catch data for the Northeast Atlantic, 4 species, herring, cod, mackerel, and capelin, constitute over 50% of the catch since 1950. 14 species constitute 80% of the historical catch, and 50 species constitute 95% of the historical catch. The 174 stocks assessed by ICES constitute 90% of the total potential catch. This is illustrated in this figure, where the species are ranked in order of catch, and the cumulative percentage of catch up to and including that species is shown. The most important species, Atlantic herring, constitute 20% of the total catch. Adding Atlantic cod brings us to 30% of the total catch, and the first 20 species constitute 85% of the total catch. So in any analysis dealing with the potential yield of these fisheries, we must be clear whether we are giving all stocks equal weight or considering the importance of the larger stocks. If our concern is yield and food production, we have to consider the size of the stocks. So let us look at the trends in abundance. For the assessed stocks, the trends in abundance are shown in this figure. The total estimated abundance declined from about 110 million metric tons in the early 1950s to a low of 46 million metric tons in 1990, but has since grown to 62 million tons in 2014. So why have the stocks declined and then increased? The answer is quite simple. Fishing pressure was too high, up to about 2000. With improved management, fishing pressure has been reduced and abundance is increasing. The fraction of the total biomass of the fish that was caught increased from about 10% in 1950 to an average of 25% from 1970 to 1995, but has since declined to a little less than 15%. A central feature of most national and international legislation is the concept of maximum sustainable yield, or MSY, as the goal of MSY management is to maximize long-term catch and stock health. For any given fish stock, there are 3 associated quantities: MSY, UMSY, and BMSY. MSY is the average tonnage of fish that can be caught each year in the long term on a sustainable basis. Associated with MSY is a rate of harvesting, commonly called UMSY. UMSY is the fraction of the population harvested each year that will produce MSY. Finally, there is BMSY, the average biomass the stock would be at if it was harvested at UMSY. For most stocks, we can estimate MSY, BMSY, and UMSY. Plotting UMSY against BMSY gives us what is known as a Kobe plot seen in this figure. In this plot, each stock is a circle. The size of the circle is proportional to the MSY for the stock, so the big stocks are the big circles and the small stocks are the small circles. To maximize long-term sustainable yield, the stock should be near 1 on both axes, the place where the two orange lines cross, which divide the space into 4 quadrants. Quadrant A, in green, is where abundance is high and fishing pressure and low. Stocks in this quadrant are underfished, meaning there's potential for more food and money to be collected from these stocks. Quadrant B, in orange, is low fishing pressure but also low abundance. Stocks in this quadrant were probably overfished and now on the road to recovery since fishing pressure is low. Quadrant C, red, is the area of most concern, where abundance is low and fishing pressure high. Finally, quadrant D in purple is stocks that are still above BMSY but have fishing pressure higher than UMSY. Stocks in this quadrant are fine for now, but may warrant management intervention to get them closer to the intersection of UMSY and BMSY. Generally, stocks above the horizontal line will need to have fishing pressure reduced to maximize long-term yield, while stocks below the horizontal line would need to have fishing pressure increased to maximize long-term yield. Stocks in quadrant B and C would increase in abundance, that is, move to the right, if fishing pressure set to UMSY. Stocks in quadrant B need to rebuild in order to achieve their potential, but they would rebuild even if fishing pressure was increased to UMSY. They will rebuild faster if fishing pressure is kept below UMSY. Fisheries management is largely about controlling the rate of harvest. What managers generally seek to do is keep the harvest rate at or near UMSY. This figure shows the median U divided by UMSY, and it's quite close to the is quite close to the MSY target exploitation rate currently, but many individual stocks are above or below that level. In this graph, as in the next few, each stock is given equal weight, whereas in earlier figures dealing with biomass and catch, the larger stocks had more influence. Here we see that from about 1970 to 2000, the median fishing mortality rate was about 1.4 times UMSY, too high to produce maximum yield, but beginning about 2000, the fishing mortality rate declined so that it's now at or near UMSY. The decline in fishing pressure we see in this graph is quite a bit stronger than the declines we saw earlier in the figure showing fraction harvested. This is because the really large stocks in the Northeast Atlantic, which dominate the earlier figure, were not as overfished and have seen less reduction in fishing pressure. But on average, across all assessed stocks, fishing pressures declined about 33% since the mid-1990s. Using BMSY as a reference point, we see stocks decline to below BMSY until about 2000 and then begin to recover and are now on average just below BMSY. So let's now discuss potential yield. So what's the potential of these stocks to produce more fish in the catch? The answer is quite simple. Stocks that are fished too hard need to be fished less, and stocks that are lightly exploited need to be fished harder. We can calculate how much yield would be produced at current fishing pressure for each stock, and how much it would increase for stocks that need to have fishing pressure reduced, and how much potential increase from stocks there would be for stocks needing to be fished harder. We can get an idea of this by comparing the size of the stocks above and below the horizontal line in the figure we saw earlier. We see far more large stocks below the orange line, fishing pressures too low, compared to large stocks above the orange line. The next figure shows how much yield could be obtained at current fishing pressure, exactly 10 million tons almost, and how much could be increased by fishing the stocks above the line less, that's about 0.7 million tons, and how much catch could be increased by fishing harder on stocks below the line, that's 2.9 million tons. Though management can and should reduce fishing abundance in stocks above the line, to maximize yield, we would need to increase fishing pressure in underexploited stocks, which would create more jobs, provide more high-quality nutrition, and increase revenue. The current catch is only about 8 million tons, although we estimate that at current fishing pressure, yield will rise to 10 million tons. Under current fishing pressure, almost all stocks that are now below BMSY will increase in abundance, and thus catch will increase. This figure shows the Kobe plot shaded by what fraction of the potential yield is obtained at the current fishing mortality rate. Points shaded dark green achieve greater than 90% of the potential yield, and differing shades indicate decreasing proportions of potential yield being achieved at current exploitation rates. To achieve maximum yield, stocks above 1 on the y-axis need to have fishing pressure reduced, and those stocks below 1 should have fishing pressure increased. Clearly, both should be done, and we estimate catch could rise to 13.6 million metric tons. So some final cautions. These calculations of potential yield are predicated on two key assumptions. One is that the objective is to maximize the tonnage landed for each stock, and two, that each stock can be managed individually. Neither of these is likely true. Management goals are often a mix of maximization of yield, reduction of the costs of fishing, decreasing ecosystem impacts, and a range of social goals. Society and fisheries managers may choose to forego some potential yield for other purposes. So the calculations we presented need to be regarded as what-if questions. If the goal was only to maximize yield, then some stocks need to be fished harder, some to be fished less. Many fish stocks are harvested in mixed stock fisheries, where it's impossible to harvest each stock at its target exploitation rate. This is particularly true for demersal species caught by trawling, such as cod and haddock, where many species are caught in the same location with the same gear. Thus, it's generally not possible to apply a specified exploitation rate that's distinct for each stock. In summary, overall, European Atlantic fisheries are improving and on average are well managed. Some stocks do need a reduction in fishing pressure, but what will surprise many is that to maximize yield from these fisheries, there is more potential yield from increasing fishing pressure than from reducing it. Again, I want to emphasize that we definitely need to reduce fishing pressure on the stocks that are currently fished hard, but the potential increase in yield from this action are not very large.